Somewhere in our galaxy, a dead star is firing a laser beam that scientists couldn't explain for years, and the answer just rewired what we thought we knew about the universe's most extreme power plants. This isn't science fiction. It's a real class of stellar corpses called white dwarfs, and one of them, roughly 380 light-years from Earth, is whipping electrons to nearly the speed of light and blasting them at its neighboring star every 2 minutes, like clockwork. Here's what a white dwarf actually is. When a star like our Sun runs out of fuel, it doesn't just fade away. It collapses into an object about the size of Earth, but packed with a mass hundreds of thousands of times greater. In one famous case, the white dwarf star AR Scorpii is about the size of Earth, but with 200,000 times its mass. Imagine squeezing something as heavy as our entire Sun into a ball you could drive across in a single day. That's the density we're talking about. Now pair that collapsed monster with a second, smaller star, a red dwarf, cooler and dimmer than our Sun. In the system AR Scorpii, this rapidly spinning white dwarf star is powering electrons up to almost the speed of light, and these high-energy particles release blasts of radiation that lash the companion red dwarf star, causing the entire system to pulse dramatically every 1.97 minutes. That's not a metaphor. One star is physically being struck by a beam of radiation from its dead neighbor, over and over, forever, like a cosmic lighthouse with a body count of 1. But here's where it gets even stranger. For years, astronomers kept finding other binary pairs like this one, white dwarfs locked in orbit with small red stars called M dwarfs that were pulsing out powerful bursts of radio waves. These stellar pairs pulse with radio waves every few minutes over spans of hours, gaps far longer than the rapid radio pulses from spinning neutron stars, or pulsars, which repeat within mere seconds. Nobody could explain exactly how two stars orbiting each other were generating something that behaved like a laser beam shooting straight into space. That mystery just got solved. In August 2026, researchers at Caltech ran supercomputer simulations that finally cracked the mechanism. Using these simulations, they laid out a clear picture for how the interacting white dwarf and M dwarf binaries power beams of intense radio light that shoot into space. The mechanism has a name: electron-cyclotron maser instability, or ECMI for short. And here's the part that should blow your mind. This exact same process already exists right here in our own solar system. ECMI occurs throughout the universe, around stars and planets, and even in Earth's auroras. It involves electrons spiraling through magnetic fields in a way that produces radio emission, and it's most famously behind the intense radio bursts observed between Jupiter and its moon Io since 1955. Think about that for a second. The same physics lighting up the northern lights on Earth, and the same physics crackling between Jupiter and one of its moons, is scaled up to stellar proportions somewhere out in the galaxy, turning two collapsed and dying stars into a functioning cosmic radio transmitter. Back in 1969, Caltech physicist Peter Goldreich and the late Donald Lynden Bell proposed that as Io sweeps through Jupiter's magnetic field, it generates a powerful current, a tube of electric flow measured in the millions of amperes, between the moon and the planet's magnetosphere. That prediction was later confirmed by direct satellite imaging. 57 years later, that same 1969 theory just explained something happening trillions of miles away, between two dead stars. Here's how it plays out. In these binary systems, the white dwarf and the red dwarf are roughly the same mass, but the white dwarf, the burnt-out cinder of a star that once looked like our Sun, is far smaller in size. As the two stars circle each other, in one confirmed case, once every 2 hours, the orbital motion generates a powerful electric current, exactly like Io does with Jupiter, only on a massive scale. Electrons caught in that current become unstable, and that instability triggers a laser of radio beams, technically called a maser, that fires out into space. And it never actually switches off. Lead researcher Yiqi Zhang explained it simply. The maser is always on. We just see it when it swings around and points toward us, which is why we detect it as a pulse instead of a constant beam. It's not blinking, it's rotating, like a lighthouse beam sweeping past a ship at sea, except the lighthouse is a dead star, and the beam is powerful enough to be picked up by radio telescopes on Earth. The numbers get even wilder. The simulations showed that this beam-generating mechanism can be up to 10 times more efficient at producing radio signals than scientists had previously believed. That means these stellar pairs are pumping out more raw power than anyone had calculated, quietly, from systems we'd been staring at without understanding what we were seeing. And this isn't some rare, one-off freak of the universe. Astronomers have identified this same category of object, called long-period radio transients, from just a handful of remote regions of our galaxy, with only about a dozen confirmed so far. One of them, a system called ASCAP J745-5051, was confirmed to consist of a white dwarf, a dense stellar remnant roughly the size of Earth, but with a mass close to our Sun's, paired with a red dwarf companion around 1/10 its mass, actively pulling material from its neighbor. Every single one of these strange, slow-pulsing radio sources scientists have found in the past few years traces back to the same basic ingredient: a dead star locked in a gravitational dance with a smaller, living one. So why does any of this matter to you, on a planet 380+ light-years away from the nearest one of these things? Because it means the universe is still running experiments we haven't finished decoding. A theory written in 1969 to explain a moon and a planet in our own backyard just turned out to describe a phenomenon happening between dead stars across the galaxy. The physics of Earth's auroras, Jupiter's magnetosphere, and a stellar corpse blasting its neighbor with near-light-speed electrons, it's all the same underlying rulebook, just written at wildly different scales. And this discovery didn't come from a telescope spotting something new. It came from scientists finally running the numbers precisely enough, with powerful enough simulations, to explain data that had been sitting there, unexplained, for years. That's the quiet, unglamorous side of huge discoveries. Sometimes the mystery isn't out there waiting to be found. It's already in your data, waiting for someone smart enough to model it correctly. Somewhere out there right now, a dead star the size of Earth but heavier than anything you can picture is spinning, dragging its magnetic field through space, generating a current, and firing a beam of radio light at a smaller star that never asked for it. And it has been doing this for who knows how long, completely unnoticed, until we finally built the tools to listen. If you had to guess, what do you think we'll find hiding in the next mystery signal from deep space? Drop your theory in the comments. And if this kind of real, mind-bending space science is your thing, follow this page so you don't miss the next one.